Quantum entanglement. You've heard of it, right? It's one of the most mind-bending ideas in all of science. This strange, almost telepathic link between particles. But what if the biggest secret of this spooky action isn't about the vast distances of space, but about the incredibly tiny moments of time? All right, so let's get right into it. We're going to start with the classic picture of entanglement, the one that famously baffled even the great Albert Einstein. So the idea is, on one hand, pretty simple, but on the other, it's just completely profound. You have two particles, born from the same event, and they become linked. If you measure a property of one, say its spin, you instantly know the spin of the other, even if it's clear across the galaxy.
And for, decades, we've always just assumed this connection is perfectly instantaneous. But here's a fascinating question. What about the moment of creation? How long does it actually take for this entangled state to form in the first place? Does this spooky link just, poof, appear out of nowhere?
Well, it turns out a really groundbreaking experiment just put that exact idea to the test, using a stopwatch so precise it can actually measure the birth of a quantum connection. So you've got these researchers in Vienna who set up this really clever experiment. They fired a laser pulse at an atom, creating an entangled pair of electrons. And their goal, this is the key part, wasn't to measure the speed of the connection across space, but to actually time the process of entanglement itself. How long does it take to come into being? And here's the kicker. The process? It wasn't instant. It actually had a duration. In their experiment, the entanglement took about 232 attoseconds to fully develop. And an attosecond, it's an almost impossible to imagine slice of time. Think about it like this. There are more attoseconds in a single second than there have been seconds in the entire history of the universe. It's just, wow. We're talking about the fundamental timescale of how electrons even move. Now, let's be really clear here. This doesn't break physics, okay? The correlation between the particles is still, for all intents and purposes, instant. No signal is zipping across space faster than light. What this research shows is that the act of the particles becoming entangled, that process itself has a measurable physical duration. It's a subtle difference, but it's a profound one. The fact that entanglement takes any time at all, that's a massive clue. It tells us it's a physical process, right? Not just some abstract math trick. And this has opened the door for a totally radical new way of thinking about entanglement, a theory from physicist Umair Abbas-Siddiqui that shifts the entire conversation from space to time. At its core, Siddiqui's hypothesis is that we've been looking in the wrong place this whole time. He's suggesting entanglement isn't a link through space, it's a link through time. In simple terms, it's about particles finding a common rhythm. Their internal quantum clocks get perfectly synchronized, like they're vibrating to the exact same beat through the fabric of time itself. Okay, think of it like this. Imagine you have two identical tuning forks. You strike one, and what happens? The other one starts vibrating too, right? Because they share the same resonant frequency. Siddiqui is proposing that entangled particles do something very similar, but their connection isn't carried through the air. It's a shared vibration, a shared rhythm through time. It's the same idea of resonance, just applied in this incredibly fundamental way. So, if this whole temporal resonance idea is right, it could fundamentally change not just our picture of the quantum world, but maybe reality itself. So, to get a feel for how this temporal resonance might work, let's try a little visual metaphor. Imagine a single quantum potential. Just think of it as a point of pure possibility, appearing out of a total void. Now, this point isn't just sitting there. It starts to oscillate, to pulse, sending out these waves in time, just like ripples spreading across the pond. This is the particle's temporal vibration. And eventually, these waves, these oscillations, they interfere with each other and lock into this stable, coherent pattern. This beautiful, symmetrical form is like a visual metaphor for how two particles born from the same event could find and lock onto a shared rhythm in time and achieve entanglement. And the implications of this are just huge. First off, relativity is safe because nothing is actually traveling through space faster than light. Instead, space-time itself might be the medium for this resonance, which then suggests we could one day tune entanglement with super precise energy pulses, almost like tuning a guitar. And maybe, just maybe, the act of measuring a particle is what knocks it out of sync, what breaks that beautiful resonance. So where does this all leave us? Well, it paints this beautiful and just profoundly different picture of the quantum world. What we're really seeing here is a huge shift in thinking. The whole mystery of spooky action at a distance starts to transform into this incredible vision of a harmony in time, a synchronized dance happening on a scale so fast we can barely comprehend it.
You know, the legendary physicist Richard Feynman once used this beautiful metaphor to describe the elegant principles that underpin our entire universe. And maybe that's the ultimate takeaway here from this new frontier of physics. This research suggests that the deepest, most mysterious connections in our universe, they might not be about the distance between things at all, but about the rhythm they share. A universe woven together not by threads of space, but by stitches in time.